Yeah, Rajat.
Sir, all the dialectic proportional to your classroom frequencies and all is actually related.
Yeah, sure.
What's the effect on it?
Yeah, sure. Yes, this is the actual equation. This is your free electron density and your electric charge, and this is the frequency spectrum, the normalized frequency spectrum of the visible spectrum, omega. Omega means between the plasmonic resonator on the surface, you have these atoms that are vibrating at different frequencies. The incident frequency kind of distorts the normal equilibrium resonant frequency of the electrons within the surface atom, and that actually changes the material properties of the device. So that's the reason why it actually depends on the plasma frequency and also on the incident radiation. Any other doubts? Even if it is not.
There was one problem that on slide DQ.
Detuning.
Cycle.
Yeah. Detuning is nothing but it is offset from the central frequency. For example, see if you see here, I'm not plotted the actual range. I just normalized it from 0 to 4. So detuning is essentially the offset from 0. That is, this is your 0. I've normalized it to 0. Offset from 0 is just the detuning part. That is offset from the central reject factor. Any other one? That's a very good question. As I said earlier, the plasmonic resonators are narrow band structures, and until now, the highest field concentration and absorptivity is obtained using plasmonic resonators. So until now, they are not used plasmonic resonators in a big way in solar energy conversion. The reason because it is, they were not able to fabricate these devices and also design these value of the conduction band and the top of the value of the conduction band, I'm sorry, and the top of the valence band are in the same order. Here the x-axis is your k, which stands for momentum. Whereas in your indirect band gap materials, what happens is that these are not aligned in the same line. So these have a separate gap. What happens in solar cells is that you have an incident radiation H2. This kind of excites the electrons from this band onto the top band, the conduction band. And once it gets excited, there is a potential that is being created, V. So it is this potential that we make use of in solar photovoltaic cells. Whereas in indirect band gap materials, what you do is there is another entire different field called as band gap engineering. You use different combination of materials to create exotic energy bands, and you have excellent properties like as I said, metamaterials and all those kinds of stuff. What happens here is that once it gets excited, you also need some sort of momentum to excite the electrons onto the conduction balance. This momentum is either given in the form of input energy, in the form of vibrations or chemical reactions, and all that. For example, like you might have seen a sort of device in the form of a tube. You kind of break that and it emits light, right? I think some of you might have seen that device. What happens is that is essentially an indirect band gap material. What happens when you break the tube, there is a sort of a chemical reaction going on. And that chemical reaction kind of provides additional momentum, not the energy, but momentum transfer. And those electrons get excited and emit light in the fluorescent spectrum. Fluorescent. That is the thing.
This obtain energy, I have obtained my energy, as you mentioned, I am the part of obtaining my energy.
Right.
I have obtained my potential. Now this potential can be stored.
Yes, sure.
How?
You store this potential in the form of regular batteries and stuff and all like that, but the problem is that using batteries is again environmentally degrading. The current batteries, because they're all the most efficient batteries are lead acid batteries kind of thing. So until now the technology is such that an efficient storage device has not been found.
So now,
It's not efficient.
you mentioned earlier, if my, suppose if I say 100% of my solar energy is being instead of my solar panel,
Right.
how much of that should be, in terms of efficiency, how much is
Very low. It's very low. Right now silicon-based devices which we see in India is around 18% maximum. The theoretical maximum efficiency itself, that is, you get it from mathematics, and that is a sure constraint that you cannot go above that particular efficiency.
I actually read an article, something related to solar, I believe from University of Missouri, which have developed a solar panel, which has been filament sheet, which contains nanoantenna, which are able to absorb 90% solar energy.
Yeah, that's right.
And as it was, very less of it has been absorbed. What makes this different that it can absorb more parts?
Yeah. The thing about, you talk about nanoantennas, right? The other name for these plasmonic resonators in the visible spectrum are nanoantennas. They're called as visible spectrum antennas. Unlike your antennas which generally emit radiation or receive radiation in the microwave or the radio spectrum, these are already radiation in the visible, not in the visible spectrum, sorry, radio or deep infrared or also microwave waves. These are in the visible spectrum. So these are called as visible antennas. It's the same thing.
One more thing, you mentioned about silicon-based observer as well as organic-based observer. Why not try polymer-based observer? Because there are certain, I believe, usual material of indium tin oxide. There are certain polymer-based electric observers that have been developed from, I believe, from the University of Princeton. So if people are developing these, how efficient are these compared to the normal?
It is it has very low efficiency. You have silicon-based active devices.
But we the stage of VKC of the silicon.
Yeah, it does. But if you look into the efficiency,